So I have a friend who also teaches organic chemistry, and she had her students get this question and a problem, and we were talking about this question, and I was like, well, how about I kind of go over this question with my class too? So in this problem, you start out with this E alkene, and so remember, E alkene means your two highest priority groups are on opposite sides of that double bond. So we see a methyl on one side and a propyl on the ethyl on the other side. And so because they're on opposite sides, when we do a concerted electrophilic addition, your stereochemistry must be conserved. So the methyl and the ethyl have to still remain opposite to each other. So for instance, if you did epoxidation, if you did halogenation, if you did the halohydrins, syndiols, anything that adds at the same time, hydrogenation, all of those things are going to lead you to keeping the ethyl and the methyl on the same side. So when you had those stepwise mechanisms, they can end up kind of in different locations, just because if you had a carbocation, the molecule can kind of change its position a little bit and things could rearrange and all sorts of things can happen. So in terms of stereochemistry, in syn electrophilic additions, you're going to conserve the alkene stereochemistry. It's just like with SN2 or E2, wherever the groups are in those two reactions, they have to stay there because everything is concerted. There's no time for any groups to rotate or move around. So in these this particular molecule, remember that there is those understood hydrogens, which implies that they're opposite to each other. So they have to remain in that orientation as well. So when I do my reaction, so let's say we do a bromination, the bromine is going to be attacked by the double bond, because as the double bond shifts the electron density of the bromine towards the other bromine, so whichever side it comes near to, it makes the closest bromine become partial positive, so it attacks it. But bromine has a lot of electrons, so as the double bond is sharing its electrons and starting to become positive, the lone pair attacks it. So we already talked about these in class, so you've seen this mechanism. So what's going to happen here? Then we form the bromonium ion. And so I want you to kind of imagine, if the methyl and the ethyl have to be on opposite sides of each other, they have to stay there. So the methyl and the ethyl need to remain on opposite sides of the structure. So if I give the ethyl and the methyl a wedge, they have to stay a wedge, right? Not right now. I'm not doing that right now. But if I give it a wedge, it needs to stay a wedge. If I make them dash and a wedge and a dash, it needs to stay in a wedge and a dash. But because we know that the molecule has the ethyl and the methyl on opposite sides, one needs to be a wedge and one needs to be a dash, whether or not the groups are on kind of on so even if we know that the groups are opposite side from each other, just drawing them, I would start by saying, okay, make one wedge and make one dash. So I'm going to translate it here, and I'm going to tell you why the wrong one is wrong. So I would translate this as taking either the wedge being the ethyl or the methyl. So I'm just going to say here the methyl has a dash and the ethyl has the wedge on that structure, because now that I've opened my double bond, I can have wedges and dashes. We generally don't draw wedges and dashes on double bonds because of the direction that we're looking at. The double bond, typically we look at the double bond in a flat rotation and not where it's like curved and and stuff like that. So I'm picking the methyl as a dash, so that means the ethyl has to be a wedge. So what happens to the hydrogens? So the hydrogen on the same carbon with the methyl has to be wedged then, and the hydrogen on the side with the ethyl has to be dashed. So what lines do I put on the bromine? I put straight lines pointing in the same orientation. So I would draw something like this. We can also think about it and can make Newman projections and look at it. So if you were to imagine your Newman projection as you're tacking it, so you're going to imagine like looking at that double bond kind of straight onto you. So like onto my hand, if I were to be looking at the double bond as if the double bond is my hand, if I have something pointing up from one side or something down, imagine that the carbon that you're looking at from one double bond to the next, so looking down one carbon to the next on the double bond, you're imagining that you're blocking the second carbon. And remember, because the structure is flat on a Newman projection, one hydrogen in the front will go one way, one hydrogen in the back will go the other way. The ethyl on one side goes one direction, and the hydrogen on the opposite side goes in the other direction. So you're kind of looking at it at the side. It's the same kind of idea. But we oftentimes want to just draw the stereochemistry on the bromonium part, the 3-membered ring. But here's the implication of this. If I put dashes on the bromonium first, what that's implying is that the bromine is in the same plane, which is fine, absolutely fine, because that is true. But that means I'm taking the dashes out of play when I draw the structure. And so when we draw single lines for just the regular single bond lines, when we're drawing them, even though I'm drawing, kind of implying that they're opposite to each other, how I'm drawing them, but we're kind of also implying that they're sort of in the same plane-ish. But here's the problem. When I draw it like that, that means also that my two hydrogens have to have an orientation. So my bromine is already taking the dash away. That means if I drew the ethyl and methyl, in this case I had two ethyls, if I just drew them the way that I have here, you're implying that the two hydrogens are on the same side. That is a problem. So it just turns out it doesn't work. Now, what is the implication of doing these kinds of reactions? Well, if we have an E versus a Z double bond, when we do our syn hydrogenation, well, they're all syn, but our hydrogenation where we have hydrogen gas and a metal catalyst or something of that nature, so your hydrogens are going to go on at the same time. I'm going to use deuterium just so that, because remember, deuterium is just heavy hydrogen, so that it's more clear which ones I'm paying attention to. So if I were to try to translate that into wedges and dashes, because this is kind of a little bit meaningless, I do need to put my ethyl and my methyl, or in this case 2 methyls, in the same kind of orientation. But we definitely know that the deuteriums have to be in the same direction. And then that's kind of the implication. That means the other hydrogen. So we have other hydrogens that are just like that. So we can look at doing something similarly. With the E, because they're opposites, I'm going to put those in there. So I have to apply that. And so that means the hydrogen that is on here has to be this. The deuterium has to be this. And those two hydrogens, they're in the same plane, but we have to draw it that way. So that's kind of the stereochemistry implication.